Hey everyone, and welcome back to the Deep Dive.
It's great to be back.
We're the show that, takes these huge stacks of information,
And boils them down.
exactly, sifts through all the noise, finds those golden nuggets of insight just for you. And today, we're plunging into something absolutely foundational.
Foundational, but often working completely behind the scenes, like the plumbing.
Yeah, that's a good way to put it. It's everywhere in the digital age, underpinning every informed decision, yet most people don't really see it.
Indeed. Without it, all that raw data just sits there, overwhelming, pretty much useless.
Exactly. So we're talking about ETL. That's extract, transform, load processes.
And 3 magic letters.
Right. It's how raw data, scattered across maybe countless sources, gets, cleaned up, organized, shaped.
And delivered exactly where it needs to go.
So it becomes actual valuable knowledge. So our mission in this deep dive is to demystify ETL. We'll look at how it evolved, the massive challenges it faces now with big data.
Oh yeah, the scale is incredible now.
Yeah, totally. And the ingenious ways experts are optimizing it. We've pulled together a ton of research papers, industry analysis, technical breakdowns.
The real mix.
Yeah, to give you a really comprehensive but hopefully engaging understanding. This is all custom tailored to help you quickly grasp what's most important in this field. You could almost say we're helping you become, well, the data benders.
I like that. Bending data to our will.
Okay, let's unpack this then.
The foundation, what is ETL and why does it matter?
All right, to kick us off, let's start with the basics. Imagine you're not just a chef, but like the head chef for a massive global restaurant chain.
Okay, big operation.
Huge. Managing thousands of ingredients coming from all over the place, different suppliers, and each needs its own special prep before it can go into hundreds of different dishes.
Complex logistics.
Right. And everything has to be perfect, consistent, on time. You wouldn't just, dump everything from the delivery trucks onto the plates, would you?
Definitely not. Chaos.
Exactly. There's this really sophisticated process. You got to source the ingredients, clean them meticulously, chop, season, follow the recipes.
All that prep works.
And then finally assemble it into something delicious and crucially consistent, night after night.
That's a perfect analogy, because in the world of data, ETL is precisely that sophisticated multi-step process. Formally speaking, it refers to these software modules, these pieces of code
Right.
that are specifically responsible for getting data into usually a data warehouse, populating it with operational data.
Okay.
But the key is, this data doesn't just get dumped in. It undergoes a whole series of precise transformations on its way there.
The prep work.
Exactly.
So-
Making sure it's clean, fit for purpose, reliable for whoever needs to analyze it later.
Got it. And those 3 letters, EPL, each one stands for a critical stage, right? Like the different stations on that production line.
Correct. Let's break them down.
So first up is E-extraction. This is like your global sourcing step, yeah? Gathering all those ingredients wherever they are, different farms, different storage.
That's a really good way to think about it. Extraction is all about pulling data from its original sources. And these sources can be, well, incredibly varied.
Like what?
Oh, everything. Traditional transactional systems, the databases running day-to-day operations. But also simpler stuff like flat files, maybe spreadsheets,
Okay.
or even real-time streams of data. Think IoT devices, sending readings, website clicks, data that's constantly flowing.
Wow. Okay. So the challenge isn't just getting the data, but getting it from all those different places.
Exactly. Connecting to diverse sources, doing it efficiently,
Right.
often without messing up the source systems themselves, and pulling out only the bits you actually need. That's extraction.
Okay, that makes sense. So after extraction, we get to T-transformation.
Yes.
Now, this is where the real prep work happens, right? The peeling, chopping, seasoning, turning those raw ingredients into something usable.
Absolutely. You could argue this is the heart of the entire ETL process. It's where that raw, extracted data gets meticulously cleaned up, reshaped, standardized.
Standardized, okay.
Yeah, making sure it meets the specific requirements of wherever it's going, like that data warehouse. And it's not just one simple step. It's really a whole suite of activities.
Like what kind of activities?
Well, for starters, you have things like schema transformations. This means fundamentally changing the structure of the data.
How so?
Maybe pivoting rows into columns, which
Yeah.
can make data much better for certain types of analysis. Or normalizing data structures, making sure things are consistent, reducing redundancy across different tables, making it tidier.
Right, tidying up the structure. Makes sense. What else?
Then there's the really crucial stuff, cleansing activities. This is absolutely vital.
Cleaning. like getting rid of errors.
Exactly. Detecting and handling duplicate records. Correcting errors, think misspelled names, wrong postcodes, inconsistent date formats. Checking for integrity constraint violations. Imagine trying to analyze sales data if customer names are spelled 10 different ways.
Right.
Total nightmare. Cleansing irons all that out. Ensures the data quality you need for reliable analysis. Sometimes, if data has really bad values, you might even move it to a sort of quarantine area, an error schema, so it doesn't pollute the main flow.
Ah, isolating the bad stuff. Smart.
Very. Then there's filtering. This is a big one for performance.
Filtering, like only keeping what you need.
Precisely. Blocking unnecessary data from going any further. Allowing only data that meets specific criteria to pass through, maybe based on a date range, a specific product line, whatever.
Like that chef only taking the freshest vegetables.
Exactly. Don't process what you don't need. The earlier you filter in the pipeline, the less data you have to handle later on. Saves huge amounts of time and resources. Rejected data might just go to an error log for review.
Okay, that seems critical for efficiency. What else falls under T?
Well, you've got sorting and grouping. Organizing data, maybe alphabetically or numerically to make it easier to work with, or preparing it for aggregations like calculating total sales per region. You need to group by region first. You also often apply function applications. This could be using built-in functions the ETL tool provides for common tasks, or it might involve running custom scripts, maybe written in Python or Java for more complex logic.
So you can add your own special recipes.
You can. Or even calling external libraries for really specialized stuff, maybe like geocoding addresses or something.
Okay.
And there are simpler foundational things too. Unary operations, things like selecting specific rows based on a condition, checking if a critical field is null, making sure primary keys are unique, or projection, which is just selecting specific columns you want to keep.
Basic building blocks.
Exactly. And to make all this repeatable and efficient, especially in big organizations, ETL tools often use templates.
Reusable patterns.
Yes, reusable designs for data types, functions, even entire sequences of activities. They let you customize common tasks and build new pipelines much faster without starting from scratch every single time, like having standard prep steps for common ingredients.
That makes a lot of sense. So that's the T. Huge amount goes on there.
It really is the engine room.
Okay, so after extract and transform, we finally get to L loading. This is the plating, right? Putting it all together, ready to serve.
Correct. Loading is the final step. This is where that processed, transformed, cleaned up data gets moved into its final destination.
Which is usually?
Most commonly, a data warehouse, or maybe a smaller, more focused data mart designed for a specific department or purpose.
Okay.
Once it's loaded, the data is organized and structured in a way that makes it really accessible and efficient for analysis, ready to inform those critical business decisions we talked about. And it's important to stress, ETL isn't just some technical detail. It's really the core component of any decision support system. Without good ETL, you can have all the data in the world, but it's just noise.
Right.
All the data that's actually going to be used for analysis, for informing strategy, for making those big calls, it absolutely has to pass through an ETL process first. It's what turns raw, messy operational data into coherent, trustworthy insights.
So for you, the listener, the big takeaway here is that ETL isn't just shuffling data around. It's the strategic engine that transforms raw information into the fuel for smart decisions. Companies that master this, they're not just tidying data. They're building a fundamental advantage in how quickly and accurately they can understand their business and their market. It's the difference between guessing and knowing.
And it's interesting, the history here. ETL processes, in some form, have been around for, well, over 40 years.
Wow, really? That long?
Oh, yeah. Initially, it was all custom scripts. People just wrote code to move data for specific needs. Then came specialized tools. But the fascinating part is, academic research on ETL, it only really started picking up in the early 2000s.
Decades.
Decades after industry was already heavily relying on it. So there was this big gap.
What did that mean in practice?
It meant that early ETL designs were based much more on practical experience, rules of thumb, good practices learned the hard way.
Tribal knowledge, almost.
Yeah. Kind of, yeah. Rather than being guided by rigorous, formal methodologies or widely accepted standards like you might see in other engineering fields.
That's quite a gap. Thinking about that lag, what do you think was the biggest headache or inefficiency caused by industry sort of figuring it out on the fly before the academics really dug in?
That's a really good question. I'd say probably the biggest cost was the lack of consistency and reusability. You had different teams, even different developers, essentially reinventing the wheel over and over again.
Building their own custom solutions every time.
Exactly. Highly customized, often poorly documented ETL pipelines for each new project. This led to this fragmented mess where processes were incredibly hard to maintain, really difficult to troubleshoot when something went wrong.
And probably impossible to scale easily.
Absolutely. Imagine every restaurant in that global chain using slightly different undocumented recipes and kitchen tools. Total chaos to manage quality and efficiency. So, yeah, higher development costs, much longer implementation times, constant battles with data quality because things weren't standardized.
Yeah.
It just made it harder to trust the final output, the insights.
Navigating data changes incremental loading and slowly changing dimensions.
Okay, this is where things get really dynamic, right?
Yeah.
Because business data isn't static. It's not a photograph. It's more like a movie.
Constantly changing, yeah.
Companies get new customers all the time. Employees switch roles. Product prices go up or down. So how do you keep that data warehouse, that analytical view, up to date? You can't just tear it down and rebuild it every night, surely. That sounds like a disaster.
It would be, especially with today's data volumes. This is a really critical challenge. When that source data changes, you need smart ways to update the data warehouse efficiently. But there's another layer too. You have to decide how to handle the change. Do you just overwrite the old information? Or do you need to preserve the history of that change for analysis? That decision is key.
History matters.
It often does. And this whole problem leads us straight into two really important concepts: incremental loading and slowly changing dimensions, or SCDs. Traditionally, yes, sometimes people did try to refresh a data warehouse using what's called full reloading.
Wiping the slate clean and loading everything again.
Exactly, reloading the entire target table in the warehouse from the source. But as you said, with data sizes exploding, data arriving faster and faster, complex structures, full reloading just becomes incredibly inefficient. It's too slow, too resource intensive. It just doesn't work anymore for most large systems.
Like trying to reprint the entire library catalog every time a single book is checked out.
Perfect analogy. It's just not practical. So that's why incremental loading is the go-to approach now.
Focusing just on the changes.
Exactly. Instead of moving everything, you focus only on capturing and processing the changes, the new records, the updates, the deletions that have happened since the last time you updated.
So instead of repainting the whole house for one scuff mark, you just touch up that spot. Makes way more sense.
Precisely. And the impact is huge. It significantly cuts down the time your ETL process takes, the latency, because you're dealing with a much smaller volume of data flowing through extraction, transformation, and loading.
Okay, but how do you know what's changed? How do you find just those new spots?
Good question. There are several clever techniques used to identify exactly what's changed in the source systems. One common method is the snapshot differential. Here, during extraction, you take a full snapshot of the source table at that moment.
A picture of the data.
Right. Then you compare this new snapshot with a snapshot you took previously, say, the day before. The differences, new rows, changed rows, deleted rows, are what you process.
Comparing two pictures to see what's different.
Okay. Another very common way uses time-stamped indexes, often called audit columns. Many operational systems are built to automatically record when a row was last updated. They might have a last modified date column.
Built right into the source system.
Often, yes. The ETL process can then just query the source table asking for all rows where that timestamp is later than the last time the ETL ran. Very efficient way to find recent changes.
Leveraging what's already there. Nice.
And then there are database triggers. These are a bit more involved. You can set up special pieces of code in the source database that automatically run or fire whenever something specific happens, like a new row being added or an existing row being updated or deleted.
So the database tells you when something changes.
Essentially, yes. The output of these triggers, maybe writing the changes to a separate log table, can then be picked up by the ETL process. It gives you a very direct way to capture modifications almost as they happen.
Okay, those methods make sense. And the benefits seem obvious. Less data to move, faster updates. Your data environment feels much more agile, right?
Definitely. Much more responsive.
But what's the catch? What's the trickiest part of making incremental loading work reliably in a big, messy, real-world company? Where do people stumble?
That's a really crucial point. The benefits are huge, but the trickiest part is guaranteeing complete and accurate change capture. It sounds simple, but it's easy to get wrong.
Missing changes.
Exactly. If your chosen method, whether it's timestamps, snapshots, triggers, misses, even a single relevant change, Your data warehouse starts drifting out of sync with the source, it becomes inconsistent.
And then your analysis is wrong.
Precisely. Unreliable insights. Some common traps include things like inconsistent audit columns. Not all source systems have reliable timestamps, or maybe they get updated in weird ways.
Okay.
Handling deletes can be tricky too. Sometimes deleted records just vanish from the source. How do you know to mark them as deleted or inactive in the warehouse? You need specific mechanisms for that.
Tracking the ghosts.
Kind of, yeah. And if your source data structure is really complex, spread across many related tables, just figuring out all the downstream impacts of a single change can be surprisingly hard.
A ripple effect.
A big ripple effect. And finally, while incremental loading reduces the main ETL workload, the change detection mechanism itself, especially triggered on very busy tables, can sometimes add performance overhead back onto the source system if you're not careful. It's a balancing act.
Okay, that makes sense. So that's incremental loading, handling the flow of changes. What about the other concept you mentioned, SCDs, slowly changing dimensions?
Right, so slowly changing dimensions, or SCDs. First, remember what dimensions are. They're those lookup tables holding the descriptive attributes, the who, what, where, when, why about your core business facts.
Like customer details, product categories, store locations, that kind of thing.
Exactly. Customer ad, product category, employee department. Now, sometimes these attributes change, but not very often. They change slowly.
Like a customer moving house, maybe. Not every day, but it happens.
Perfect example. Or an employee changing department. When these dimensional attributes change infrequently, we need specific strategies, the SCD types, to handle these updates. And crucially, we often need to do it without losing valuable historical context.
Right. Back to the history question. Let's take your example. Your customer, Jane Doe, lives in New York. Next year, she moves to London. The year after, Paris. How do you track that? Do you just update her record to say Paris, erasing the fact she ever lived in New York or London? Or do you keep track of that whole journey? Maybe knowing her location history is really important for analyzing her buying habits over time.
That's the exact dilemma SCDs are designed to solve. And the analytical need, what questions you need to answer, dictates which approach you take. The industry recognizes several SCD types, each with trade-offs. Types 1 and 2 are the most fundamental.
Okay, type 1.
Type 1. Overwrite, simplest approach. The new data just overwrites the old data in the dimension table. So Jane Doe's record, her city just gets updated to Paris.
Oof. London and New York are gone.
Gone from that record, yes. The advantage is it's easy to implement, and it keeps the size of the dimension table, the cardinality or number of rows, unchanged. The huge disadvantage: historical data is lost. Forever. Any analysis you run later will only see the latest value.
When would you ever use that then?
Maybe for correcting genuine errors, or for attributes where history truly doesn't matter. But often, history does matter.
Which brings us to
Type 2, new record. This is the workhorse when preserving history is critical. Every time a designated Type 2 attribute changes, like Jane's city, you don't overwrite. You create a whole new row in the dimension table for Jane.
a new record for the same person. How do you tell them apart?
Good question. This new record gets a new unique identifier, usually called a surrogate key. It's an artificial key, just a unique number separate from her customer ID that lets us track different versions of her record over time.
Versioning.
Exactly. And the old record, it's not deleted. It's marked as expired or not current. Maybe you update an end date column on the old record to show when it stopped being valid, or you flip a is current flag from yes to no.
So you end up with multiple rows for Jane. One for NY, one for London, one for Paris, each with date ranges.
Precisely. This method preserves the complete history perfectly. You can see exactly where she lived and when. You can analyze sales based on her location at the time of the sale.
That sounds powerful. What's the catch?
The catch is dimension growth. If attributes change frequently, your dimension table can get really big really fast because you keep adding new rows. This can impact query performance down the line if you're not careful with indexing and querying.
More data, potentially slower queries. A trade-off.
Always a trade-off. There are other types too, less common. Type 3 adds a new column to store the previous value, preserving limited history. Type 4 splits current and historical data into separate tables for faster querying of current data. Type 6 is a hybrid, combining elements of types 1, 2, and 3.
Okay, a whole toolkit.
But the core decision is almost always Type 1, overwrite, lose history, simple. Or Type 2, add row, keep history, potentially more complex. Do you prioritize data preservation or dimension size and query speed? The answer depends entirely on what your business needs to analyze.
The brains behind the operation, metadata, and architecture.
Okay, so we've got the data flowing, we're handling changes, but how do we actually understand all this data? If data is the story, then metadata must be like the instruction manual, right? The index, the who's who and
Oh,
what's what.
absolutely. Metadata about data is incredibly crucial. Without it, your data warehouse is just a giant pile of numbers and text with no context, no meaning. It's metadata that defines the structure, the meaning, the lineage, the quality rules, everything you need to actually use the data effectively.
So it's not just for the techies.
Oh, not at all. It's vital for everyone. We can actually break metadata down into different types, serving different needs. You've got source system metadata describing the original databases or files, then data staging metadata, info about data as it moves through temporary ETL areas. DBMS metadata, the database's own catalog of tables, columns, indexes, and front room metadata connecting the warehouse to the reports and dashboards users actually see.
Okay, different layers.
Exactly. And then there's more specific stuff. Business metadata is huge. This provides the business definitions, the context from the source systems, a data dictionary for the warehouse, logical maps. It translates the technical stuff into terms business users understand. What does customer tier 3 actually mean for sales strategy? Business metadata tells you.
Bridging the gap.
Precisely. Then you have technical metadata. This is the deep dive stuff for developers.
Yeah.
System inventories, detailed data models, the precise definitions of every field, the business rules applied during transformation, how it's all built.
The blueprints.
The detailed blueprints. And critically, there's ETL-generated metadata. This is stuff the ETL tools often create automatically as they run.
Like logs.
Logs, yes, but more structured. Job execution details, when did it run, how long did it take? The specific transformation logic applied. Which batch of data was processed? Records of data quality errors encountered. Performance stats. This is goal for auditing, troubleshooting, and optimizing the processes.
Understanding how the engine is running.
Exactly. And having standards, especially simple things like consistent naming conventions across all this metadata and using it for impact analysis, figuring out what breaks if a source sysl changes. These are vital practices enabled by good metadata management. It really is the unsung hero. Now, managing all this complexity, especially in large organizations with potentially thousands of ETL jobs, it requires structure. Frameworks and models have been developed to help.
Like architectural patterns.
Kind of. For example, a research tool called ArcTeller 2 implemented a formal logical meta model. Think of this as an abstract blueprint, a standard way to represent any ETL process. It formally defines the core pieces, the data stores, the activities like cleansing, joining, their inputs and outputs, their parameters.
A universal language for describing ETL.
Exactly. And a core idea in ArcTeller 2 was promoting reusability through templates. We mentioned templates earlier. These are like pre-built customizable components for common data types, functions, or activities.
Like Lego blocks.
That's a great analogy. If you often need to clean customer addresses in a specific way, you build an address cleaning template. Then you can just drag that block into new pipelines and maybe tweak it slightly instead of rebuilding it from scratch. Saves time, ensures consistency.
So the meta model is the overall blueprint of the legacy, and templates are the prefabricated building blocks you snap together.
Excellent way to put it. And tools like ArcTeller 2 often provide graphical interfaces, letting you visually design these workflows, zoom in and out, and even automatically check for inconsistencies in your design.
That Lego analogy really helps visualize it. So if the meta model is the blueprint and templates are the blocks, what's the biggest headache engineers face when trying to build and maintain one of these complex data factories? Is it keeping the blueprint up to date?
That's a huge part of it, yes. Keeping the blueprint, the metadata, and the understanding of the flows accurate as things inevitably change is a massive challenge. But I'd say maybe the biggest headache is managing the interdependencies.
How everything connects.
Exactly. In a complex ETL environment, changing one small thing, a field in a source system, a business rule, and a transformation can have unexpected ripple effects far downstream, potentially breaking dozens of processes or reports.
Domino effect.
The potentially catastrophic domino effect. Tracking those dependencies accurately, understanding the impact of a proposed change before you make it, that requires incredibly robust, well-maintained metadata and a clear view of the overall architecture like that meta model provides. Without it, making changes becomes incredibly risky and time-consuming. Balancing reuse with customization is also tough. Too many templates can make simple things complex. Too much custom code is a maintenance nightmare. Research has also tried to bring more structure by creating an ETL activity taxonomy, a way to formally categorize all the different types of operations. An activity is described by its providers, its inputs, which could be data from other activities or source record sets, and its consumers, its outputs, flowing into other activities or target record sets.
So, defining the connections formally.
Right. For example, an activity called computed discounts might take customer data and product data as providers and produce order adjustments as a consumer. This helps map out the flow clearly. Within this taxonomy, they define specific types, like filters again. Formally, a filter is an activity designed to block records that don't meet a criterion, letting only the valid ones pass through, maybe sending the rejects to an error output or, as mentioned, a quarantine schema. And to handle the sheer scale, ETL processes are often thought about hierarchically. At the very bottom, you have atoms. These are the fundamental indivisible operations, the simplest possible step, like checking for a null value or selecting a single column.
The absolute basics.
Then you combine atoms into molecules. An ETL molecule is a larger construct, maybe a sequence of a few related operations often found together in code, like a small self-contained script doing one specific task.
Okay.
And finally, you compose these molecules and atoms into compounds. A compound represents an entire workflow, often visualized as a graph showing how all the different activities and data record sets connect and flow together.
Atoms, molecules, compounds. Like chemistry for data flows.
Exactly. It's a layered approach that helps break down incredibly complex processes into more manageable parts, making them easier to understand, design, and potentially optimize.
Supercharging data flow performance and optimization.
Okay, so we've built our data factory, we understand the architecture, but now we need it to run fast. Implementing and maintaining a data warehouse, particularly the ETL part, is consistently flagged as the most demanding piece.
Demanding how?
In terms of resources, CPU, memory, disk I/O, in terms of cost development time, hardware, software licenses, and in terms of time, how long it takes to actually get the data processed and ready. ETL just eats up a huge chunk of everything.
So optimization isn't just a nice to have, it's absolutely essential for it to be viable.
It really is.
Because in today's world, speed is everything, right? If your data isn't fresh, if it takes hours or days to get insights, you're falling behind. Stale data leads to bad decisions or missed chances. So how do we crank up the speed on these ETL engines?
Well, the good news is, even though it's complex, there are many well-established techniques to significantly boost ETL throughput and slash that processing time. These are the kinds of things you should be asking about in your own data setups. A major focus is always reducing input-output, I/O contention. Bottlenecks happen when too many processes are trying to read from or write to storage at the same time. Optimizing disk layouts, using faster storage like SSDs, maybe scheduling I/O-heavy jobs carefully can help.
Smoothing out the traffic to the disk.
Exactly. Similarly, eliminating unnecessary database reads-writes is key. Every time you hit the database, it takes time. If your ETL process is constantly reading and writing intermediate results back to the database, it's going to be slow. Streamlining the flow to minimize those hits helps a lot.
Makes sense.
And we keep coming back to this one because it's so powerful. Filtering as soon as possible.
The ultimate efficiency hack.
It really is.
Yeah.
Don't drag data through multiple complex transformations if you know you're going to throw it away later. Filter it out right at the start, maybe even during extraction if possible. The impact on downstream performance is enormous. Less data, faster processing.
Simple but effective. What else?
Partitioning and parallelizing. This is fundamental for big data. Break down large data sets or complex tasks into smaller, independent chunks.
Divide and conquer.
Precisely. Then you can process those chunks simultaneously, in parallel, maybe across multiple CPU cores or even multiple machines in a cluster. It lets you scale your processing power to match the data volume. If you're dealing with summary tables or aggregates, updating aggregates incrementally is crucial. Instead of recalculating, say, total monthly sales from scratch every day.
Just add today's sales to the running total.
Exactly. Much, much faster for large aggregated data sets. Also, just being smart about extraction. Taking only what you need. Don't extract all 100 columns from a source table if you only need 10. Reduces data volume right away.
Be selective up front.
Right. And when it comes to the load step, using bulk loading utilities provided by databases is often way faster than inserting rows one by one. Sometimes you can even eliminate logging temporarily for these bulk loads, which speeds things up further, though you need to be careful about recovery if something fails.
Trading some safety for speed?
Potentially, yes. It's a trade-off. Similarly, you can sometimes drop database constraints and indexes before a massive load, let the data flood in without checks, and then rebuild the indexes and re-enable constraints afterwards. Again, faster loading, but requires careful management.
More trade-offs.
Always. Other things include eliminating network traffic. If you can process data closer to where it lives, you save time sending it across the network. And finally, letting the ETL engine do the work. Modern ETL tools and databases are highly optimized. Using their built-in functions for joins, sorts, aggregations is often much faster than trying to code that logic yourself in a script. Leverage the power tool.
Use the optimized machinery. Okay, that's a great list of general strategies. Any more advanced tricks?
Yes, research has gone deeper. Sometimes modeling ETL optimization is a kind of state space search problem.
Meaning?
Meaning you think of your current ETL workflow as one state. The goal is to find a different state, a different sequence of operations that produces the exact same result. It's semantically equivalent, but runs faster. You explore different possibilities by applying transitions.
Changing the workflow structure.
Right. One common transition is a swap. Can you swap the order of two adjacent steps? For instance, you have a step that selects certain rows, a filter, and another step that selects certain columns, a projection. Does it run faster if you filter first, then project? Or project first, then filter?
Does the order matter that much?
It absolutely can, especially with large data. If the filter removes 90% of the rows, do that first means the projection step has much less work to do. Swapping unary operations like selections, projections, null checks, function applications to find the optimal order can yield real speedups.
Finding the best sequence.
Exactly. Another type of transition is coupling or serial composition. This is about formally combining smaller sequences of operations, those molecules we talked about, into larger, potentially more efficient blocks if their inputs and outputs match up nicely. It helps structure the optimization. And a key insight from all this research is just how much physical optimization matters. Pushing selections, filters as early as possible is almost always a win. But also, sometimes adding an operation can speed things up overall.
Adding something makes it faster. How?
Strategically adding a sorter step. Sorting data takes time, yes. But if you have expensive operations later on, like complex joins or aggregations, having the data pre-sorted can make those operations dramatically faster, especially after data cleansing and integration. The cost of the sort is outweighed by the savings later.
Interesting. Pay a small cost up front for a bigger win later.
Precisely. It highlights that it's not just what you do, but critically when you do it in the flow.
Like that well-choreographed dance again. Every step in the right order for maximum efficiency. It's optimizing the flow, not just the individual moves.
That's a perfect way to summarize it. The sequence is often paramount. However, it's still true that ETL design often lacks that universally rigorous methodology. A lot still relies on experience, those best practices.
The art alongside the science.
You could say that. It's not always a purely mathematical optimization problem in practice, which does raise the question, can we automate more of this complex choreography, especially now? And that leads us right into the really modern challenges and solutions. Big data and real-time ETL optimization. The game changes completely here.
How so?
Because the sheer volume of data is immense. The variety structured, unstructured, semi-structured is huge. The velocity data streaming in constantly is intense. And ensuring veracity, the trustworthiness of that data, is harder than ever. These views of big data break traditional ETL approaches, batch processing once a day. Often not good enough anymore.
I mean, faster, more scalable solution.
Exactly. This has driven the rise of real-time ETL systems. Moving beyond batch, these systems aim to extract, transform, and load data with minimal latency seconds or even milliseconds.
For things needing instant reaction.
Precisely. Fraud detection, dynamic pricing, real-time recommendations, monitoring industrial sensors, situations where insights are needed now. And to handle the sheer scale of big data, processing paradigms like MapReduce became foundational.
MapReduce. Heard of it. How does it help ETL?
It's brilliant for parallelizing tasks. It breaks down a massive data processing job into many small, independent tasks. Mappers handle initial processing on chunks of data, things like standardizing, cleansing, filtering. They run in parallel across potentially hundreds or thousands of machines.
Okay.
Then, reducers take the outputs from the mappers and merge or aggregate them to produce the final result. It's inherently scalable need to process more data. Just add more machines to the cluster.
Built for parallel processing.
Exactly. And this led naturally to cloud-based ETL frameworks. Tools built on technologies like Apache Hadoop, Apache Spark, Apache Flink, running on the cloud. Solutions like Cloud ETL, PETL, and just using native cloud services like AWS Glue or Azure Data Factory have shown they can be vastly more efficient and cheaper than traditional ETL tools for large-scale data. The performance gains can be orders of magnitude.
Leveraging cloud scalability.
Absolutely. And there are even more specialized approaches like Big ETL, which thinks about distributing the ETL work across multiple dimensions, across processes, across functionalities, vertically, horizontally, to really fine-tune parallelism for big data's specific characteristic.
Getting really granular with optimization.
Yes, and this whole shift has also popularized an alternative pattern, ELT.
VLT, swapping the TNL.
Exactly. Extract, load, transform. Instead of transforming data before loading it into the warehouse,
You load it first.
you extract the raw data and load it directly into a target system, often a data lake or a modern cloud data warehouse. Then, you use the massive processing power of that target system to perform the transformations in place.
Why do that?
Several reasons. It leverages the scalability and power of the target system, like Snowflake, BigQuery, Redshift. It's often better for handling diverse, schemaless data found in data lakes. You load everything first, then figure out how to transform it. Reduces data movement, too.
Processing where the data lands.
Right. And that ties into another trend, UDF-fueled in-engine ETL. Modern data engines are getting really good at running complex user-defined functions, UDFs, directly inside the database or processing engine.
Custom code running inside the engine?
Yes, because a lot of complex ETL logic isn't easy to express in standard SQL. These UDFs let you write that procedural logic, maybe in Python or Java, and run it right next to the data, inside the highly optimized engine. This avoids moving data out, processing it, and moving it back in. Plus, it benefits from engine features like vectorization and JIT compilation. It can be incredibly fast.
So it's like sending the transformation recipe to the data instead of hauling the ingredients back to your kitchen, data bending right inside the engine.
That's a fantastic way to put it. Bringing the computation to the data, leveraging the power of modern distributed systems, it's a huge shift in how complex ETL gets done efficiently at scale.
The tools of the trade and the future landscape.
Okay, so we've talked concepts, challenges, optimization. What about the actual tools people use? The ETL market is pretty broad.
Yeah, what's out there?
Well, broadly, you have the established commercial GUI-based solutions, graphical user interfaces.
The ones with drag and drop interfaces, point, click, build your pipeline visually.
Exactly. These have been enterprise workhorses for years. Tools like IBM InfoSphere Data Stage, SAS ETL Studio, SAP Business Objects Data Integrator, BODI, Microsoft SQL Server Integration Services, SSIS, Clover ETL. There are many.
What are their strengths?
They usually offer very comprehensive features out of the box, often high performance, scalability, and importantly, strong vendor support and documentation. They're designed to handle complex enterprise integration scenarios reliably.
Makes sense for big companies. What's the downside?
The perceived downside, often, is flexibility or customization. While they handle common patterns well, if you have really unique, complex transformation logic, it might be awkward or even impossible to implement cleanly within their visual paradigm. And, of course, they often come with significant licensing costs.
Right. So the visual approach can sometimes feel limiting.
It can. And that limitation, plus the cost factor, has driven a lot of interest, especially in research and among developers, towards programmable code-based solutions.
Writing the ETL logic directly in code.
Yes, using libraries or frameworks in languages like Python, Java, or R. The advantages are huge flexibility. You can code almost anything potentially lower cost. Many are open source. Sometimes faster execution for specific, optimized tasks, and often better maintainability if your team is comfortable with code.
So for those situations where the standard GUI tools don't quite fit, or for teams that prefer coding, developers roll up their sleeves and build it themselves using these libraries.
Precisely. And there's some really notable open source code-based ETL tools out there. For Python developers, there's Pygmetal. It's been around since 2009, continuously updated, known for being very Pythonic, fitting well with Python's style and ecosystem. Another popular Python one is Petal. It's recognized for having a really wide variety of built-in transformation functions, making data manipulation and cleaning quite straightforward in code.
Python seems popular here.
Very. But there are others. Scriptella is Java-based. It uses XML files to define the ETL tasks. But the actual transformation logic can be written in SQL or scripting languages like JEXL or JavaScript. Quite versatile. And some benchmarking studies have actually shown RETL, for the R language, to be particularly fast for certain types of ETL workloads, making it interesting for performance-sensitive tasks, especially if you're already in the R ecosystem for analytics.
Okay, so a real choice between visual tools and code-based frameworks. Depends on the team, the task, the budget.
Exactly. But then The cloud and big data really shook things up again, leading to a new generation of platforms designed specifically for that modern world.
Platforms built for scale and cloud-native features.
Right. And when people evaluate these, they're looking at criteria like, how well does it scale? Can it handle real-time streams? How complex are the transformations it supports? Is it reliable? Secure? What's the cost model? How easy is it to use?
Makes sense. Who are the big players there?
Well, you still have established vendors adapting. Informatica Power Center is widely used, known for being user-friendly but also scalable, with strong real-time features, often seen in large enterprises. Talend Open Studio stands out as a powerful open-source option, offering great flexibility, strong processing, and broad connectivity. Very popular.
Open source is appealing.
Definitely. Then you have the cloud giants offerings. AWS Glue from Amazon is a serverless ETL service.
Serverless meaning?
Meaning AWS manages all the underlying infrastructure for you. You define the job, and Glue automatically provisions resources, runs it, and scales as needed. You pay for what you use. Tightly integrated with the AWS ecosystem, obviously.
Convenient if you're on AWS.
Very. Microsoft's equivalent is Azure Data Factory, ADF. It's their main cloud data integration service, again offering robust processing, scaling, and deep integration within the Azure world, the orchestrator for Azure data pipelines.
Okay, AWS and Azure covered.
Oracle has Oracle Data Integrator, ODI. Very powerful, especially if you're heavily invested in Oracle databases, praised for advanced features, but costs can be a significant factor. And Petag Data Integration, now part of Hitachi Vantara, is another strong player, good at handling large data sets and complex transformations, often used in hybrid cloud on-premise setups. Again, cost is a consideration compared to some open source or serverless options.
Wow, it really is like each cloud provider built their own specialized superhero for their ecosystem, plus you have these other powerful independent heroes too, a diverse toolkit for data vendors.
It is a diverse landscape. And it's still evolving. We're seeing this major shift away from just traditional data warehouses.
First what?
Towards concepts like data lakes and now lakehouses.
Okay, data lakes. Heard that term a lot. How's it different from a warehouse?
Think about how a traditional warehouse works. It usually enforces a strict structure before you load data. You define the tables, the columns, the data types up front. That's called schema on write. And it typically stores structured, processed data.
The organized library model?
Exactly. A data lake is different. It follows a schema on read approach.
Meaning you figure out the structure later.
Right. You dump all kinds of data into the lake, first structured, semi-structured, like JSON or XML, totally unstructured, like text documents, images, videos, often in its raw or near raw format. You store it cheaply, usually in cloud storage, like Amazon S3 or Azure Data Lake Storage. Then when you want to analyze it, you apply the structure or schema needed for that specific analysis.
So total flexibility on what you store, like that vast reservoir catching everything.
Exactly. Great for exploration, machine learning, storing massive volumes cheaply. But there's a catch.
The data swamp problem.
That's the risk. Because lakes often lack the strict governance, data quality enforcement, and transactional guarantees, like ACD properties, of a warehouse. They can become messy, unreliable swamps if not managed carefully. Hard to find things, hard to trust the data.
Okay, so the warehouse is reliable but potentially rigid. The lake is flexible but potentially messy. How do you get the best of both? Is that even possible?
That's the goal of the lakehouse architecture. It's a newer hybrid approach trying to bridge that gap.
Lake plus house?
Kind of. It aims to implement the core functionalities of a data warehouse, things like AC transactions, schema enforcement, data versioning, indexing for performance directly on top of the low-cost, flexible storage of a data lake, often using open formats like Apache Parquet or Delta Lake.
So structure and reliability on the lake.
That's the idea. You get the cost-effectiveness and flexibility of storing all your data in the lake, but you add layers of management and features that provide the reliability and performance previously associated only with warehouses. You can curate raw data into structured, reliable tables within the lake itself.
Best both worlds, potentially.
That's the promise. It's particularly well-suited for the cloud, allowing different tools, BI tools, SQL engines, ML frameworks, to access the same underlying data stored reliably in the lake without creating multiple siloed copies. It's a really significant evolution in data architecture.
The human element management and continuous improvement.
So we've covered technology, architecture, tools, But none of it works without the right people and processes. The human element is absolutely paramount in ETL.
Right. The tech is only as good as the team using it.
Exactly. Yeah. Effective ETL, especially at scale, requires dedicated leadership, really meticulous planning, and critically highly qualified developers who have strong database skills and understand data modeling and quality principles.
So it's not just about knowing the ETL tool. It's deeper expertise.
Much deeper. You need people who understand the data itself, the business context, and the downstream analytical needs. And you need good management practices.
Like, what kind of practices make the difference? What separates the smoothly running data factories from the ones constantly putting out fires?
Several things are key. Enforcing standardization is huge. Consistent naming conventions, standard approaches to common tasks. It makes everything clearer, easier to maintain, easier for new people to understand.
Avoiding that reinventing the wheel problem.
Exactly. Monitoring and auditing is non-negotiable. You need to track every ETL job execution, what ran, when, how long it took, how many rows went in and out with their errors, and then publish those stats. Transparency builds trust and helps spot problems early.
Keeping tabs on the machinery.
Absolutely. Maintaining documentation is vital too, but often neglected. Documenting the logic, the dependencies, the business rules. It's the institutional memory. Without it, troubleshooting or enhancing processes becomes a nightmare later on. And we talk about metadata, making sure it's not just created, but actively used and maintained is crucial. Also, a principle of keeping it simple. Overly complex ETL is hard to manage and debug. Aim for clarity and maintainability. And finally, viewing optimizing throughput as a continuous process, not a one-off task. Always looking for ways to make things run faster and more efficiently.
Constant refinement.
It has to be, because the sheer complexity of it all.
Mm-hmm.
Think about all the different operations, the dozens or hundreds of systems connected, the different modes, batch, streaming, on-demand, and often you have conflicting goals.
Like performance versus maintainability, or cost versus fault tolerance.
Exactly. Trying to manually manage and optimize all of that, juggling those trade-offs across a large ETL environment. It's incredibly challenging, maybe even impossible to do perfectly by hand.
So the scale and complexity just overwhelm manual tuning. How do we get smarter about this? Can the system learn to optimize itself in a way? Can the data teach us how to bend it better?
That's exactly where things are heading. Emerging solutions involve things like recommenders and cost models.
AI for ETL.
Kind of, yeah.
Yeah.
Using machine learning algorithms. These systems analyze all that metadata collected from past ETL executions, the runtimes, the row counts, the errors, the resource usage. They learn patterns.
Learning from history.
Right. And based on that learning, these recommenders can suggest alternative versions of your ETL workflows that might be more efficient. They use libraries of cost models that estimate different kinds of costs, maybe the actual monetary cost to run a job on the cloud, or performance costs like latency or resource consumption.
So it might say, hey, try swapping these two steps. Our model predicts it'll save 10 minutes and use less CPU.
Precisely that kind of actionable recommendation. And to feed these systems, monitoring agents are critical. These agents sit alongside your ETL processes, constantly collecting detailed performance stats.
Gathering the raw data for the learning algorithms.
Exactly. Number of input rows, output rows for each step, execution time per step, memory used, all that granular data. This allows the system, or the engineers using the system, to pinpoint bottlenecks accurately and drive that continuous improvement cycle we talked about. It creates a powerful feedback loop: run, monitor, learn, recommend, improve, run again, towards smarter, maybe even self-optimizing data flows.
Wow, that's fascinating, using the data about the process to improve the process itself. Okay, we have covered a lot of ground today. We've really taken a deep dive into the world of ETL, from those basic steps, extract, transform, load,
The fundamentals.
to navigating those tricky changes with incremental loading and slowly changing dimensions. We've seen how these carefully crafted data processes are really the unsung heroes behind smart decisions.
We explored the architecture, the vital role of metadata, the data about data, and looked at all those clever optimization tricks, especially how things are adapting for big data and real-time needs.
Yeah, and the tools. From the visual GUI-based ones to the code frameworks and the big cloud platforms now dominating the landscape. Plus that look towards the future with data lakes and the emerging lakehouse architecture.
Trying to get the best of both worlds there.
Right. Our mission today was really to give you a clearer, deeper understanding of how raw, messy data gets artfully shaped into reliable, actionable knowledge. Hopefully you feel better equipped to understand this crucial part of our data-driven world. maybe even ready to do some data bending yourself.
It's a critical skill set now.
It really is. In a world absolutely swimming in data, maybe even drowning in it sometimes, the real power isn't just having the data. It's the ability to skillfully extract it, transform it meaningfully, and load it effectively to uncover insights.
Turning noise into signal.
Exactly. So the final thought for you to chew on is, how will you use this understanding? How will you apply these ideas, whether you're building systems or interpreting their results, to shape the data stories of tomorrow? Thanks for joining us on the deep dive. Remember, the more you learn, the more you realize how much more there is to know, and finding that out is the real reward.